Hello, my name is Šeněk Albl and I will talk about our work on reconstructing 3D flight trajectories from multi-camera networks. We present a fully automatic method that reconstructs the 3D trajectory of a moving object while calibrating the multi-camera system in both space and time. Our pipeline takes only 2D image coordinates as an input and produces the camera pose parameters, the time shift and scale between camera streams, and the 3D trajectory of the object. The motivation for having such system is the fact that the amount of drones in the air grows quickly and will accelerate even more thanks to applications like package delivery or people transport. The drones, however, can also cause damage, whether by accident or by an intentional attack. It is clear that the drone air traffic will need to be regulated, and we will need a way to enforce the regulations and avoid dangerous situations. A system that tracks the position of airborne vehicles is therefore necessary. Moreover, many applications would benefit from having a localization system that is more accurate than regular GPS, usable in GPS-denied environments, or in case we want to track drones whose data we do not have access to. We argue that an effective system that is deployable on large scale should be accurate, reliable, cost-effective, not polluting the electromagnetic spectrum, easy to deploy, easy to calibrate, and recalibrate when conditions change. Existing radar and radio systems do not satisfy these properties, and we show that multi-camera systems can. Looking at some existing work in camera 3D tracking, there has been an attempt at using total stations equipped with cameras to automatically track planes. This is, however, a very expensive system with limited speed of tracking and hard to deploy permanently. In small indoor areas, we can use well-developed motion tracking systems. Unfortunately, those are not only very expensive, but also require active illumination and target markers, and therefore are not usable outdoors. The question that our work aims to answer is, can we do the same as the expensive motion tracking systems, but with affordable hardware, in an uncontrolled environment, and on large scale without complicated installation procedures? In order to achieve that using multi-camera network, we should be able to calibrate and synchronize the system using preferably nothing else than the moving targets. Calibration of a multi-camera network using moving targets has been investigated already in 2005. Svoboda has shown that it is possible to achieve spatial calibration by using a moving dot created by a laser pointer. This work, however, dealt with precisely synchronized cameras only, which is not a very practical solution for low-cost systems and over large areas. Noguchi presented a first attempt at both spatial calibration and temporal synchronization, and this work was further improved by NIST in 2009. Both methods can estimate the time shift between camera streams, but they require a very good initial guess and are sensitive to outliers. They also do not optimize the 3D trajectory. These are the closest related works. In our CVPR 2017 paper, we have shown how to estimate the two-view camera geometry and time shift robustly using RANSAC. Vo in 2016 has shown a bundle adjustment method to handle moving objects with motion regularizers. And Rozantsev presented a method to perform spatial calibration and 3D trajectory reconstruction using drone data. Sadly, each of these methods has its limitation or restrictive requirement that makes it impractical. In our method, we utilize the good parts of each and eliminate the bad ones. We believe that our work contributes in three ways. The first is the method that estimates the camera poses, time shift and scale between the image streams, and highly accurate 3D trajectory of the moving object. Each of its parts is robust to outliers, does not require initialization of the camera poses or timing, and is able to handle a rolling shutter. Second contribution is the experimental part with precise ground truth, which proves that high accuracy is achievable with budget equipment in large uncontrolled environments and without complicated calibration procedures. All this by using just the 2D detections of the moving object as the input. As a third contribution, we make the code and data freely available. In our problem, we observe a moving object that is captured by multiple cameras. The object's immediate 3D position, denoted capital X, is projected by perspective projection into a 2D image point. We have n cameras, each described by the parameters of a 3x4 camera matrix Pi. Each camera captures frames at times Tij, where j is the index of the frame. The frame time can be expressed in global timeline using a timeshift parameter beta and timescale parameter alpha. The task is, given 2D observations xij, find the camera matrices pi, the synchronization parameters beta and alpha for each camera, and the trajectory of the object is expressed as 3D points xij that correspond to the 2D observations. Assuming we start with a sequence of observations in each camera, we first try to obtain temporally consistent matches. We do this pairwise for each camera pair. In the second camera, we fit splines through the continuous parts of the trajectory. Then, we establish correspondences by sampling the spline in the second camera at times that correspond to the observations in the first camera. We then use our previously published minimal solver to estimate the epipolar geometry of the camera pair as well as the time shift. Thanks to the minimal solver, we can do this robustly in Ransack to eliminate outliers. After a robust estimation, we refine the parameters further using nonlinear optimization on all inliers. Then we update our initial guess of the timeshift beta. Having the pairwise geometry and the time mapping parameters, we can triangulate the 3D points using standard techniques such as direct linear transform. Then we fit splines through the reconstructed 3D points. The spline is parameterized by the global time. We use the splines to establish 3D to 2D correspondences between reconstructed trajectory and a new camera. These correspondences are used to compute the camera absolute pose by a standard perspective endpoint. After connecting a new camera, we can add new parts of the trajectory by establishing the 2D to 2D correspondences with existing cameras as in step 1 and triangulating as in step 3. Gradually, we build up the trajectory using all available data. Same as in Visual SLAM or Structure from Motion. After each step, we run bundle adjustment, which is a nonlinear optimization of all parameters. In standard bundle adjustment, the camera and point parameters are adjusted by minimizing the reprojection error over all observations. In our approach, we replace the individual 3D points by splines that are parameterized by time. Instead of adjusting the 3D coordinates of the points, we adjust the control points of the spline. Basically, the spline is sampled at a given time of each observation to obtain a 3D point, which is then projected to the image plane. In the work of WO, a version of bundle adjustment is presented that treats each observation as an individual 3D point, but on top of that adds a regularizer that minimizes either the velocity or the acceleration of the object. We found this formulation to be unstable for reconstruction from the moving object only, without the static part of the scene. Instead, we retain the spline formulation that constrains the trajectory well and add the motion regularizers on top of that. We minimize the sum of the reprojection error and the motion regularizer over all camera parameters, time shifts and scales, spline parameters, and rolling shutter rates. Rolling shutter is a method of exposing the image sensor sequentially, line by line. Thus, while the first line is already being read out, the second line can still be exposed, which increases the maximum possible frame rate and exposure time. It is important to realize that rolling shutter is being used in vast majority of cameras produced today. The drawback is that each line is basically captured at a different time, which affects the location of moving objects in our scenario. In order to accommodate for this difference, we add another term to the function that maps the observation time to the global time. It is now dependent on the row on which the observation was made and the rolling shutter scan rate. To the best of our knowledge, there was no dataset for the given problem with precise 3D trajectory ground truth. Therefore, we created several datasets ourselves. To obtain a precise ground truth for the 3D trajectory, we used the newly released real-time kinematic system from the company Fixed Position, which claims to have 1 to 3 cm accuracy. Subframe time synchronization ground truth was obtained by radio synchronized LED flashes visible in all cameras at the same time. For one of the datasets, we also measured the camera positions using high-precision GNSS station. Although not used in our work, we also provide a hand-labeled 2D locations of the drone, useful for training detectors. In our datasets, we try to cover various scenarios with respect to drone speed, size of area covered, number of cameras, and weather conditions. We obtained 4 datasets in total, which are sorted in range from easy to difficult. We also used a wide variety of cameras, from low-end smartphones and compacts to more expensive mirrorless camera and even a GoPro action camera with wide field of view, to be able to demonstrate the universal applicability of our method. To compare our method to the closest alternative of Rosancev 2017, we used their dataset as dataset 5. We present results in terms of 3D trajectory error and number of outliers, which is the ratio of points which are outside the confidence interval of 3 times the root mean square error. On the easiest dataset, we achieved incredible accuracy with mean error less than 10 cm. In datasets 2 and 3, we achieved mean error of 20 cm or less, and on the most challenging dataset, the mean error was less than 40 cm. We did observe an overall improvement with using the motion priors, especially on the challenging datasets. Introducing the rolling shutter had mostly negligible impact, apart from the most challenging dataset, where the variant with least force prior and rolling shutter provided significantly better results. Here are the visualizations of the results on each dataset. Note that our result is mostly indistinguishable from the ground truth, which is due to the reconstruction being so accurate. This is the most challenging dataset, with a lot of missing data due to misdetections or the drone going out of sight. Here you can already see some difference on the result compared to the ground truth. This is the result on dataset 5 provided by the authors of Rosancev 2017 paper. We achieved 2 times better root mean square error on this data than they did. The ground truth for this dataset was, unfortunately, obtained using only regular GPS sensor on board of the drone, whose accuracy we cannot estimate. It is visually observable, however, that the quality of our result is significantly better. Here is an example of qualitative difference without using the motion prior on the left and with using it on the right. The marked parts of the trajectory are significantly distorted, but get corrected by the least force prior. We also performed an ablation study that shows the effect of the individual parts of the pipeline that optimize the synchronization parameters. This highlights the importance of proper temporal calibration. The columns of the table represent increasing initial desync between cameras in frames, while the full pipeline manages to achieve stable performance regardless of the initial desync. The pipeline without the initial pairwise timeshift estimation, only with the band adjustment temporal optimization, fails to reconstruct properly anything beyond 5 frames timeshift. The pipeline without any timing parameters adjustment does not work at all, even with the timeshift of 5 frames. We would like to point out the interesting results that one can take away. Highly accurate 3D trajectory reconstruction is achievable even with low-cost devices. The robust time synchronization is vital in this case. Without using the static background, as is the case of cameras looking up and observing drones, the previous state-of-the-art approach is not viable. More constraints on the trajectory need to be placed, such as the spline parametrization. The motion priors, although statistically not very significant, can have a positive impact on local parts of the trajectory, especially as the data gets more challenging. The effect of rolling shutter seems to be negligible in our datasets. We assume it is due to the similar alignment of cameras that causes the drone to be detected in a similar vertical part of the image between the cameras. To summarize, we presented a novel method to robustly calibrate a multi-camera network in both space and time and reconstruct accurate 3D trajectories of moving objects. We analyzed the effect of synchronization, different motion regularizers, and rolling shutter. We have demonstrated that the pipeline can be used in a low-cost, low-effort localization system that could benefit both research and industry. We collected several unique datasets for multi-camera drone tracking with precise ground truth for the 3D trajectory, time synchronization, and 2D drone position in the image. Last but not least, we have made our codes and data freely available online. Thank you for your attention.